replicated this without any real feedback. So, okay. The content I'm going to introduce you today is in the Introduction to Statistical Learning with Applications in R. This is the main reference of the course, which is quite of a didactic book. And if you don't have much background in machine learning, I think it's a good starting point. But together with that, often there is the same material, or in a bit more in detail, there is also this element of a statistical learning book. And in general, we are going to be sharing both the chapter books on both books. So the first one is the first impression, and the second one if you want to dig in. Both of them are quite nice, so the one that you enjoy the most. Starting with an example of machine learning, which is actually the first example of the book, we are going to start with the example of the sales or advertising, where we consider that we have collected data for 200 markets. And basically what we collected is the budget that the different markets invested in advertisement, either in TV, radio, or newspaper, and how the sales of that year after this advertisement investment was for each of these, let's say, companies. So as you know, as I was saying, we are going to divide the feature space or the input variables. I sometimes want to call them input variables, sometimes feature space. So I guess over the time you will get familiar with me. With my way of speaking. Basically, in this example, we are going to consider three different inputs. The first one, which is how much money we put into TV advertisement. The second one, which is on the radio. And the third one is on the newspaper. And our goal is to see what is the effect of these investments or budgets on the sales of the company, which is the output variable. I believe that in the book, I right now don't remember how they call it. I often call it the target variable because it is the variable I'm trying to predict. I think in the book now I remember it's usually called response variable. Both of them, they have their own meaning, but basically it is what you are trying to predict. And in general, what we are going to assume is that there is a relationship from X to Y of the form of that you see at the bottom of the slide. I don't think you can see my my mouse, right? Can you see it? That is great, because yesterday I didn't manage to make it visible. So basically, we are going to assume that the relationship between the input features and the output is modeled of this form, where basically we say that the outcome or the output variable is a function of the input features plus some additive noise. And this additive noise, we assume that it's going to have zero mean. That means basically that the expected value of Y is going to be f of X. So you can see only when I move the mouse. That is good. So here we are. Okay. So in this example, the first thing that we can do is to actually plot each of these input features and the output in these 2D diagrams, where basically on the x-axis, we have the investment in one of these advertisement markets, and on the y-axis, we have the sales. And as you can see, there seems to be quite some dependence. I'm going to close my window because they just started renovation somehow. Yeah, that should be better. And if we do the same, if we now do some linear regression, actually to see this relationship of the TV with the sales, what we get is this blue line that just showed up here. We can do the same with the budget into the radio and see the relationship with the sales and do an estimation of how this relationship is, and the same with the third one. So as we can see, when we do this fitting on how the budgets actually influence the sales, we can see that in the three cases for the TV, for the radio, and the newspapers, all the sales increase as we increase the budget that we invest in the advertisement. And actually this blue line that I have been showing here, it is the result of what we call the least square linear regression, which is actually what we are gonna enter in the next lecture. So I'm not gonna really give too many details today on this topic, but that would be more for next week. This was one example where basically we saw that basically the relationship between the input features or the input variables and the output variable was linear, but there might be some other cases where such a relationship doesn't need to be linear. And here we get an example, the income example, which is from simulated data, where basically we see the relationship between the years of education and the income of these people. Right? So it seems that there is here an area where there is almost a linear relationship. So the more higher education level you have, the higher your income, your salary is going to be. But there is a point in which it doesn't seem to matter too much here how much you study. Your salary doesn't increase linearly anymore. And I would say we public professors are an example. I did my whole career, bachelor, master, PhD, everything, right? And at some point we are public workers and our salaries are capped because we are public workers, and I don't think there is much more I can do. Even if I do another PhD, my salary would remain the same. So in that particular case, as you see, if we would do some regression fitting, we would try to find a line that relates the years of education and the income, removing the noise, because the noise is these variations that we observe. We would get something that looks more like a sigmoidal form, which is clearly nonlinear, except for some small region in here. As I was saying, when we do this fitting, of course, we don't aim or we cannot expect to fit all the exact values, because the first assumption that we were having in the previous slide was that we are going to have that the outcome or the output variable is a function of the input plus some noise. This noise, we are assuming that it is with zero mean, but of course, if there is noise, we don't expect, and as we will see later in the presentation, it is better that we actually don't fit this noise, because noise is noise and there's no real good information there. So the question that one might wonder is, first of all, why do we want to actually fit this blue line, right? Or the blue lines in the previous one, which were these ones. Well, in this example, we have collected what I will call often historical data. So we have collected data about how was the relationship between advertisement investment and sales, or how is the level of study and your income. But in general, what we are going to be interested often is in making predictions, so that we can plan, for example, how much we need to invest in our advertisement in different markets in order to get higher sales. And of course, I cannot know the sales of next year until the year is not over. So what we are gonna aim is to actually find a function, which I'm gonna call f hat, which is gonna try to predict this target or output variable. In general, in this situation, we are going to assume most of the cases that all the inputs are available, and the one that the target one, the output variable, is not visible for future data. And there are two scenarios that we are going to consider here. The first one, where we just want to make predictions, so that given an input set of variables, what is the output that I might expect? And in that particular case, I won't be that interested in the particular form of this f hat function, but rather on simply knowing what is the relationship from x to y, what I might want to expect. That is one particular example, but in some application domains, you might also wonder, or you might also want to open up the black box and make it a bit wider, in the sense of being able to understand how this relationship is, because this might, for example, help you to better make decisions for the future. So in bringing an example from the book, what we get is that if we assume that we have as input the blood profile of a patient, for example, the blood pressure and the level of sugar in blood and even of fat, like cholesterol type of fat, maybe the output is the risk of having a reaction to a particular drug or treatment, or maybe you just want to predict any other like cardiovascular disease risk, right? Which in general you are not going to observe, but you just want to know the relationship input-output and get a better understanding of how the body reacts to different input features. And whenever, of course, we have an estimator, f hat of x, which we are gonna, the resulting value we are gonna call here y hat, of course, what we are gonna have is some error. And actually, if we compare the expected value of the true output variable minus the one that we predict to the square, in general, what we can do is to decompose this y, because our assumption was that this y is simply a function of x, fx, plus some noise. And then we have our estimator. And if we develop a bit further these terms, what we get is that, in fact, what we are going to have is that the square of the expected difference between this f function of our estimator of this f function plus the variance of the noise. And this variance of the noise comes from the data. So the only one that we are going to have control on is actually on this f hat. So this, of course, I'm not a big fan of all these bottom clicking, but it is okay. So when we look at these two terms here, what it is very important to notice is that this error, this overall error that we get, for example, evaluating over the overall training set, so this expectation is over all the x's and y's that we have collected in our data set. So in the example of the advertisement, that would be the 200 data points, like budgets and sales data points. What we are going to see is that in general, this mean square error is actually the difference of our estimator, and this is going to be what we call the reducible error plus the variance of the noise, which we are going to call irreducible error. Why do we call them reducible and irreducible? I mean, the irreducible one is something that comes from the data, right? So the data have some particular noise. The life is very often not purely deterministic, and you cannot exactly know how much of the sales are going to be, but just have around a value. And there is nothing we can do to reduce this error. But what the error that we can reduce by having a model which is, for example, more flexible is the reducible error. So that this one, if we have an expressive FNOF model, we could make 0, but this one can never become 0. Unless we are overfitting, which is a term that we are also going to study in a few minutes. So in general, what we are going to aim is to find an f hat function that reduces this reducible error to the minimum. That means to 0, because this I have taken the square of this real valued number, and therefore anything that I have here is greater or equal than 0. The same with the variance. So how we arrive from the expected value of the difference to these two terms is actually gonna be your homeworks for the first assignment, which, as I said, is already out. So, as I was mentioning before, you might wonder why you want to estimate F. And I think I already spoiled the reasons. The first reason is you might want to understand the relationship between input and output, so that whenever you see a set of inputs but you don't know the output, you are able to predict it. And the other reason that you may want is in order to make these predictions, in order to make decisions in the sense of how you will distribute, for example, your budget for advertisement. So this is just a predictive task, but also you might want to know or simply understand what is this relationship and know, for example, whether the more the budget, it has a positive correlation with the sales. So for example, if I increase the budget or the investment I do in advertisement, I'm gonna get higher sales. Or there is, for example, a non-linearity, like we were seeing in the example of the income, where after some level, it doesn't matter how much more I invest in advertisement, it might be that we don't get any higher sales, right? And this is a good understanding for the system, for the system owner or the owner of the company that is investing in advertisement, to better understand how to run his or her business. I'm gonna mute some people that doesn't seem to be mute. So if please remember, I cannot be on that all the time, so remember to mute yourself. Okay, good. So in general, what it is gonna happen, as we are gonna see next, is that the higher the predictive power, that means that the more complex the function, we might be to do better predictions or to make the reducible error closer to zero. But at the same time, the more complex the model, it is going to also be harder to understand how it works and how it relates the x's to the y. So if we think of a linear model, this is going to be in general very easy to understand, as we were seeing a bit before. Let me come back maybe. Because, yeah, when you see these linear fits, in here you can see that the higher the investment in the radio, TV and newspaper, the higher the expected sales, and also it seems that the slope of the former is greater than the slope of the other two, right? And this, by simply visualizing that, is very easy to understand. However, if I bring a high dimension and highly nonlinear model, so even if I have plots of this sort in very high dimensions, that interpretability might not be that easy anymore. So in general, the question that we are gonna answer in the next few minutes is, okay, how many different ways or how can I actually estimate F? So in general, we are gonna consider that we get n observations, n training data points, which actually correspond to pairs of inputs and outputs. This is what we call training, and basically we are gonna have the vector of inputs and the output of this for each of these inputs. And what we are gonna do is to find this f hat such that we in the training set f hat approximates our output variable. In order to do so, we are going to distinguish two types of models for that, or methods. One what we call parametric and one that we call non-parametric. So if we think of a parametric method, basically what we are going to assume is that there is a functional parametric form for this f hat, actually. of this form, for example. So this would be a linear parametric form because basically we are simply doing a weighted sum of the input features. And basically learning a parametric method doesn't go beyond learning the parameters of this function that we have assumed beforehand, right? So if we assume that the function of x that goes from x to the output is actually linear, of meaning of this form, and I'm given with a set of x's and y's, which would be here, everything I need to do is to learn what are the beta values that better go from x to y. So that is going to be very easy. But the problem that in general we are gonna have, not that easy, but at least it's easy to understand. The problem that we might have here is that if we assume a parametric form, that it is not the right one, right? So if we assume that the model is linear, but our data doesn't have a linear relationship, our reducible error is gonna be quite high. You can imagine the case in which we have this kind of sigmoidal data that we were seeing before, and we just try to fit a linear model. There will be some regions, the most linear region, where we are going to be doing a good job. But as soon as we go into the corners of the sigmoid, where it gets the plateau, we are going to do a very bad job there. So in order to solve that, what we can actually do is to increase the flexibility of the methods that we use, and for that we can consider, for example, non-parametric methods. So in the non-parametric methods, what we mean is that it doesn't mean that there are no parameters, but in general it means that we are not going to assume a particular parametric form on the f function, but we are going to try to learn that parametric form. And that is going to give us much more freedom. So sometimes I simply refer to non-parametric methods as functional forms with an infinite number of parameters. So the thing is that, as I was saying, if you assume no non-parametric, that doesn't mean no parameters, but it means more like infinite number of parameters, or at least a very large number of parameters. So in general, we are gonna need a large number of observations in order to do a good fitting of the parameters. And some of the other problems that we might encounter is that actually we end up doing what we call overfitting, which is no more than we actually don't explain only the relationship between x and y, but we also end up explaining the noise. So that could be an example of overfitting, where you can see that if this was the original error, you can see that there are some bars here and here, right? When I do overfitting, basically the points almost fall in this hyper surface that I'm learning. So in terms of examples, I just read a bit the chat about people asking for non-parametric. You don't need to worry, we will see some non-parametric examples in the following lectures. It is very hard to explain a non-parametric method without entering into a particular method. But don't worry, everything will come. This is only an introduction. Everything that you need to understand is that whenever we say parametric, we are gonna specify a particular form for this f hat, and therefore the number of parameters that we are gonna need to learn is determined, and everything that we are gonna do is that learning f hat translating to learning the parameters. While if we assume a non-parametric method, in general, you can consider that you might have an infinite number of parameters or a very high number of parameters, where, for example, you can think of all the a linear model combined with any kind of polynomial model, and you can go in any order and see what is the best fit of the data. And the problem that you may have with the different two approaches is that if you go for parametric models, if you did a very bad parametric assumptions, like linear, but your data are not linear, you might end up in underfitting. That simply means you don't explain very well your data. And if you go non-parametric, you can end up in the other way around, where basically you explain the information part, which is relationship X to Y, but also the noise. And the noise is something that you shouldn't be able to explain because by definition is noise. Good. So in terms of flexibility and interpretability, basically we get here a few examples that in general, of course, the higher the flexibility, the better we are gonna be able to fit the data, but the higher the risk of overfitting. So when we move towards here, right? And also in general, as I was saying, it's in general gonna be harder to directly interpret the methods as we go towards the right-hand side of this plot to better understand how this function, this f hat that we are gonna assume, relates out inputs and outputs. And this is why, as we go towards the right, the interpretability, how we can interpret the methods decrease. And coming back to examples, so if we go into the left side, we are gonna have some models, some linear models that assume only use a subset of the input features. We are gonna have the least square, which is the linear regression that I was showing you at the beginning, and which we will cover on the next lecture. But we also have some other models like trees, generalized additive models, bagging, boosting, support vector machines, and as some of you were asking, neural networks are here, right? Because we can have an arbitrarily large number of parameters. Just for your information, in general, neural nets are parametric functions, but they have a very large number of functions. Super vector machines are non-parametric. Usually we consider them non-parametric because they fall more into this concept of having an infinite number of parameters, kind of implicit. So usually the neural networks are a bit on the fence because they have such a large number of parameters that you could think that they are non-parametric, but actually whenever you define a network architecture, you are defining the parametric form on how the input and the output of every neuron relates with each other, right? It's a bit in the fence there. Okay. So in general, what is preferable? Do you want a more flexible model, even though you are gonna lose interpretability, or should we go in the other way around? Well, this is in general a very difficult question, and it depends on the complexity of the data, right? What it doesn't make sense is that if in your data, the relationship input and output is linear, you go for something highly nonlinear, because this is prone to overfitting, and there is nothing that you are gonna be able to explain either, right? Because any explanation is gonna be made up because you are even explaining the noise. So in general, making a decision of what is the best model is gonna be hard, but just nowadays that we have plenty of neural nets architectures, I would say try not to kill a fly with a gun, right? That doesn't make sense. So if you got your data, please try to study your data, see whether there are some linear relationships, you can visualize part of the data. And if you see that everything seems to be quite linear and you train a linear regression model and it's doing a quite good job in prediction accuracy or a low square error, why would you go for something more complex, right? So simply common sense is quite good. Okay. So before I move, Okay, I think I got a lot of questions on the parametric, non-parametric. This is a discussion that I wouldn't say people would arrive into an agreement. In general, the SVM is, in how I was taught about it, it is considered non-parametric. And we are gonna see it in the future. So maybe we can have this discussion about what of the methods are parametric, what are not, once we go into later into the course. But basically, in an SVM, in general, it is quite hard to write in terms of the parameters, what is the relationship input and output. And this is exactly what I meant by parametric. Okay. So in terms of supervised versus unsupervised learning, the examples I just mentioned, they were all supervised because basically what we had was an input feature X and an output or target variable Y, which we were interested in predicting. And basically we just wanna try to fit how, if there is a relationship between X and Y, we just try to fit an F hat that tries to capture that relationship. This is the standard supervised setting. If we go into the semi-supervised learning setting, what it happens is that sometimes for some of the data you get X's and Y's, but there might be for some other data that you only got the X's. And the whole idea of the semi-supervised learning setting is where you don't discard the X's for which you don't have the Y's, but you rather try to use the information contained on the X's for which you don't have the Y's in order to make also better predictions for the Y's. So, let me see, because I see some faces here that seem to be a bit worried. Imagine that for some of the companies, I see how much they invested in the advertisement. I'm the company that tells you, that recommends you where to add, how much money to invest in any advertisement, right? And I have a lot of customers. Some of these customers, when I do the recommendation to them and say, hey, this is what you are gonna invest, at the end of the year, they are happy to share with me how their sales were. But there might be some other companies that they don't want to share that information with me. But I do have their input features, right? So here I have two options. Option one, I discard all these companies of mine for which I don't know the sales and try to fit my predictor just based on that. Or I can say, well, in this X's, there might be also some valuable information because somehow the X's of some of these companies for which I don't have the Y's might be kind of similar. They might tell me something about the population of X, and I can try to exploit this information somehow when I try to train the predictor. And this is precisely the semi-supervised setting. And the last setting that we considered, sorry, I went too fast, is the unsupervised learning setting, which is maybe I don't have even a target in mind. Maybe I'm not trying to predict anything in particular, but maybe I collected a lot of data. Let's imagine I collected a lot of features from all of you, our students. So I collected data about what is your study program, what number of semesters you are here, what is your previous background, for example, which country you have studied your high school, and what was your GPA, your grades, and everything, right? And I just want to know a bit how the population of my students look like, and find some structure to see whether, for example, there are different groups, or I have for some people, I need to do a bit of extra work because maybe they are lacking a particular background, right? I just try to do a bit of understanding. An example of unsupervised learning that many of you might be familiar is the clustering one, right? So I would take all of you, and based on the features I collect from you, I will group you into different groups, sharing some characteristics. And I would say, well, now that I have my groups, maybe I need to approach these different groups differently. okay? But there is not a target variable that I'm trying to predict. Let me see. So we got a bit of questions. Okay, a lot of questions here. Okay, so with respect to transductive learning, so I would say in general, the transductive setting it's simply a way of considering different people use different terminology. So there is no black or white, right? But in general, we consider semi-supervised learning when we are when we are trying to predict a specific target. But for example, the transductive learning might be unsupervised, but maybe you don't observe all the features for everybody. And you try to simply fill up the gaps for those students that, for example, I don't have some parts of their features, I might want to fill up these gaps, but the gaps, the predictions I want to do, they don't need to be always the same features for all the students, but they might be different, right? So that is how I would use semi-supervised learning versus transductive learning, but I would say different people might use it differently. So in terms of what everybody more or less agrees is supervised, semi-supervised, and unsupervised. And if some people might disagree, for you and for the purpose of this course, this is the definition we are going to cover, so stick to it. Okay? Good. So as I was saying, an example of unsupervised learning is clustering. So if we assume I have some features, let's imagine that these are some features with your previous semester grading and your high school grading. Maybe I just wanna see whether I have different groups in this example, and basically clustering simply means somehow assigning or grouping people of similar features together. So here it's clear that we got 3. In this example here, that might not be the case, that it is so clear. Do I have 3 groups? Do I have 4, 6? Well, it depends, right? This is a potential clustering of 3, but as you can see, there is some overlaps between clustering. In general, we would like to be on the left-hand setting, often in real-world data, and mostly as we grow in dimensions, because here we only have 2. You can imagine that making these clear separations is not that easy. Or I would need to go very highly nonlinear in order to go into all the details. Okay. So the question that we haven't addressed, of course, is that I said, well, you can go parametric, you cannot go decide not to go, you can decide to go non-parametric, and depending on your data, you might need to decide. And the question is, how do we decide, right? So the first thing in terms of how do we decide is the model accuracy. And here we are only gonna measure, for now, the model accuracy on the training data. So we are gonna basically measure the mean square error, so the sum, this is the Monte Carlo estimator because we only have training data and samples, as I was saying, and I'm gonna compare the true output variable that I observe versus the one, my predictions based on my f hat, and I'm gonna square that and take the empirical mean. And this is what we are gonna call training error. So in general, what you are gonna try to do is to find the f hat that minimizes this MSE. This is how you are gonna train things. Of course, this is only for training, but in general, what you are gonna be interested is not in predicting what you already saw, but in predicting new data points. Right? So now I get a new samples x0, and I want that I didn't use to train the model to find this f hat, and I want to see how well this f hat does in this unseen data. And basically, this is what we call the test error, also generalization error or expected prediction error. I usually call it test error because it's the shorter, but all these terms are usually equivalent. And what we can see here on the right-hand side is an example where we have x's and we have y's, and we have the true function that this synthetic data has been generated, which is this gray black line, I think it's black. And then if we train a linear model, I think we are missing the linear model. Yeah, now the linear model is here. If we train a linear model, this is the best we can do. So you can see that we are not fitting very well these gray circles. We can do some non-parametric but smooth approach, which is called the smooth splines, which is this blue one, which seems to do a much better job now. Or we can go into a different type of splines, which are much less smooth and therefore much more flexible. And you can see here that it tries to follow all the points, right? It gets much more close. And this is definitely an example, as we will see, of overfitting. So I would say the blue is gonna make a good job, the best probably. The yellow, which is the linear model, is gonna tend to do underfitting because these points are clearly a way off. And the blue seems to be a quite reasonable job. Not perfect because, of course, this n that I have here is not infinite either. Right? Good. So I've been talking, of course, about underfitting and overfitting. And I think the best way of seeing this previous plot into under and overfitting is by actually plotting the flexibility, which we are going to measure as the degrees of freedom of a model. We will enter there more in detail a bit later, and the mean square error of these methods, both on training and test. Of course, the more the flexibility in training, which are these ones, the lower the error. Because as I said, I can make the error if I put a model which is very, very flexible, I can fit perfectly fine even the noise. So I can even go to 0. But the problem that I may have is that later on when I evaluate on test data, you see how badly I will be doing. And this is a clear problem of generalization of overfitting, that you are very happy, you say, hey, I got a 0 error training. Well, be suspicious. That is not the right way to go. Because then these are the kind of behaviors that you might expect in test set. So on the other corner, what we have is that basically our training and our test errors are very similar, but this is a problem of underfitting, because if we would increase a bit the flexibility of the model, we would not only do better in terms of training, but also in terms of test. And actually, this is the cherry on the top. This is the one we would like to find. And this is the one that somehow minimizes the irreducible error. There is always gonna be, as I was saying before, an error floor in the mean square error in test, which depends on the variance of the noise that you got in your data. And there is nothing you can do to solve that. Okay, so give me 1 quick minute to go. People are writing a lot in the chat. You need to understand that my multitasking is not that great. So from time to time, I will need to be moving here and back. But maybe we can go a bit more into how we assess the model accuracy and discuss a bit more the over and under fitting afterwards altogether, right? So basically, this was one example where we have a moderately nonlinear case where we were getting this kind of behavior. Of course, we can have a quite almost linear case because the true function is somewhere here, which is almost linear. And here both we expect that both the linear model and the smooth splines are going to be a good job, while as you can see, the bottom one, this one that is kind of wavy, is going to in general not be as good. And this is something that we can observe here already, where I think definitely the smooth splines does a bit of a better job in both training and test, but the difference between these two in training is not good. So probably this is a case where if you are interested in the interpretability of the model and the error, the mean square error in test is so similar, why not to go for a linear model? Less parameters, more interpretability, why not? Right? Definitely, I wouldn't go by any means to the right side of the plot. And finally, if we see a highly nonlinear model where we have this kind of behavior, basically the linear, you can imagine that as we are around 100, this is very bad. But if this example would be our example of the investment in advertisement, basically you are asking here, your prediction here is overestimated. Yeah, your prediction here is overestimated, and they would expect a much better result that they would get. So in general here, you can see that any of the splines approaches seem to be more reasonable. Still, it seems that the bottom one, the right one, has some tendency to overfitting here. That you can see very clearly when we plot again the mean square error and the flexibility in both in training and test. This is a very sweet spot because basically it says that the error that you get in training is almost the same as the one that you get in test. Good. So this is what I got in terms of models, and something that I believe it is important is that actually when we measure the test error, basically everything that we need to do is to compute the same expectation that we were computing before, the MSE, the mean square error. But this time, of course, we don't take the expectation with respect to the data in the training set, but we compute the expectation of the data in the test set. The problem, of course, is that in general, the test set or how this is going to work in practice, you don't get the Y's, but we will see later on how to deal with that problem. And let's assume that for now we got a test set. And what we can see is that if we basically elaborate a bit further this expression, basically what we obtain here is that we can write your square error as the variance of your estimator plus the bias of your estimator to the square plus the variance of the noise. Basically, this variance of the noise is something that we already talked about. When I say your estimator is your estimator of the Y's on the test set, and basically when I talk about the variance, basically it is telling you what is the systematic deviation from the true value. So if we come back to this example, right? In general, the systematic deviation would be how far you are from the actual true function. Okay? In general. While if I talk about the variance, what I mean is the variance of your estimations for different training sets. So if I would have assumed, for example, a linear model, and instead of observing my n samples, I would obtain a different set of n samples, I would get another type of another set of parameters. Right? And actually the variance of your estimator is measuring across any potential data set how much your estimations are going to vary. This is a bit intuitive behind it. Again, spoiler, you are going to have a bit of fun with this, and because you are also going to be working on that in the following days. So in general, what we are going to observe is actually that there is going to be a trade-off between the variance and the bias. So in general, what we are going to observe is that the lower the bias, the higher the variance, and in the other way around for the same class of estimators. So if we come back to our example, where we have a moderately nonlinear function, true function, what we have here is the true MSE that we were plotting before in the test set, right? This was this same shape. And what we can now do is to divide it into the two terms that we were talking about, the variance and the bias, right? The other part is simply the shift of the variance of the error, right? This is a constant which is positive. So you simply shift it up. And it doesn't depend on X. So what you get here is that when you decompose this into bias and variance, you can easily see that the higher the flexibility, in general, the lower the bias. That makes sense because the least you deviate from the true values that you are trying to predict, but in general, the higher the variance. And this is the case also in the almost linear case, where it is very clear that actually if you get a very small or a little flexible method, like for example a linear model, since your data are almost linear, you get a quite good job in terms of both variance and bias. So if you have linear data, you would like to be here, right? And if you go to the highly nonlinear case, you might get a variance and bias decomposition of this form, where, of course, in order for the variance to grow, you would need to go much more to the right side because your data were highly more nonlinear. In general, what we are going to be looking for is that our estimators have both low variance and low bias. Okay. Okay, it seems that there are some parts that are not clear, so let me try. When I talk about flexibility, is the kind of model I'm going to assume, right? So by flexibility, I mean how complex of a function I'm using to approximate this data. The most simple thing that you can be is a linear approximator, like the one that you have here. I mean, you can make it constant, but then maybe you don't learn anything, right? And then you can have arbitrarily complex models. And when we talk about the degrees of freedom, is how many parameters or how much flexible you can make the model. So maybe it is not super clear here, but here you see this. And basically, this is flexibility in the model or in the functional form of your regressor is allowing the estimator to almost follow the noise, basically, right? Of course, in general, what it is going to happen is that what you are given is with the data. And when I mean that you are given with the data, you are given with these empty circles. And what you want is to find a line, a functional form that goes as close as possible from this data, but that generalizes well. So that if I now get another data point here, I can still do quite of a reasonable job explaining it with the function I learned. So whenever I say overfit, right, it means that I did a very good job in your training data, but then when I take a new data point, x0, I'm quite likely to do a very bad job in its prediction because basically everything I did was to make my function equal to every data point. You can assume that I can make a function f hat that basically simply for every x puts a value in the corresponding y during training. This is gonna do a 0 error during training because I'm gonna basically make a function, interpolate a function like that joins the different points. But then if I add a new point that I never see during training, of course my error is gonna be greater than 0 unless I exactly get the same data point that I got before. But if we are in continuous fashion, the probability of that is gonna be 0. So we are gonna do a bad job. So coming back here, if my computer doesn't crash, good. Good. So what I said is that, of course, what we are going to be interested is in the MSE, in the mean square error on the test set, which basically takes the expectation between the true output variable and our predictions over a data set that I haven't seen during training. So for new data points that I didn't use to train my F hat. And if I play a bit with the maths, what I'm going to observe is that in general, I can decompose this into 3 terms. One, which is no more than the irreducible error, right? There is nothing I can do with that because this is the variance. And then I'm going to have the variance of my estimator and the bias of my estimator. And the question is that this MSE is going to be between variance and bias. So what it is going to happen is that if I get a very flexible model that basically pass my F hat over every training data point, the variance that I'm going to get when I change across different x0 is going to be very high because every x0 is going to be at any random point, right? And then I'm going to have a very high variance, even though my bias might be very small. So, and this is exactly what I was trying to show you here, that the MSE that I was having, I can divide it into 2 parts, the bias and the variance. And you can see that in general, the bias reduces as I increase the flexibility of the model because I basically make the data points to pass through my training data, but then the variance increases a lot because if I would train in a different training data set, I would get completely different results. I hope it is more clear. Okay, so in terms of the classification setting, so far what we have been doing is that we were assuming that we have input features and we had an output variable that was continuous and we were trying to find the relationship between X and Y. If now I assume that Y is not a numerical variable, but instead it is a categorical one, then I'm not going to be in the regression setting, but rather into the classification setting, because I'm going to try to assign every set of input features into a class. For example, if you are the students, I get your features, and maybe instead of clustering as what we were doing before, I want to classify you in terms of who is going to pass or not the exam. And that would be what I would like to predict. I'm not going to do that. That doesn't sound very fun. So in this particular setting, of course, it doesn't make sense to measure the mean square error because the Y variable is going to take a categorical value, which is, for example, binaries, either 0 or 1, or maybe it's going to say whether you belong to one of the K classes. So in general, what we consider in these classification settings is what it is called the misclassification error, which simply is the average error that you make for every data point. In this particular case, we are evaluating in the training. And of course, this is an indicator function that sum up 1 whenever Y and Y hat disagree, and it is 0 if I did the right classification. So if we look at if we can do the same, we can do the same at the test error and compute this same expectation, but over a test set or over the whole population. And in general, since this is going to be a variable, this is going to tell you what is the probability of you making a mistake. So in this context, what it is actually interesting is that there is something called the Bayesian classifier, or the Bayes classifier, sorry, which is actually the one that minimizes the test error. And it is a very simple classifier because it simply picks, given the set of features that I have observed, the class with the higher probability. So if you could compute the probability of an observation X0 to belong to each of the K classes, because not every classification problem needs to be binary, you may have K values. Basically, the Bayes classifier is going to be the one that assigns you according to your probability of belonging to each of these classes. And the good news of this Bayes classifier is that it has the minimum error, classification error. So that is the case. And the problem that you may have here is that this should be the true probability of each of your feature vectors belonging to a class. And in general, you don't observe that. You are given with X and Y's, but know how they relate with each other. So in general, unfortunately, we can never really compute the Bayes classifier unless we get synthetic data. So just to give you a bit of an example, a bit of a more visual example, now we assume that we have two variables, X1 and X2, and basically each of these observations, which are these circles, belong either to one class or another, which are the yellow and the blue ones. And basically, what we could do is that we in general observe our data, and basically you can see that it is quite hard that there are some overlaps. So here, for example, you got that we get to a yellow and a blue point very nearby with each other. So the goal of a classification problem is that if I would observe something like, my computer is crashing, that is not good. I don't have the plot here, but if I would only observe the data points, which is the training, what we would like to learn is how do we establish a division between these two classes. And in general, what we are gonna do is to try to find how do we make decisions on who we assign where. And in order to do so, what we can do is to use the method called the KNN, K nearest neighbors. So if we consider this setting, sorry that my computer is crashing, so the slides sometimes get a bit wild. In this particular example, the Bayes classifier would be the one that we observe here in this line. And this would have an error of 0.13 because, as you can see, there are some misclassifications. There are some blue dots on the other side, and there are some yellow dots here. Since we never get access to the Bayes classifier because we don't have the probability of every class belonging to every observation belonging to every class, what we can do is to, for example, compute what it is called the K nearest neighbor, which basically computes the class or predicts the class that is the majority among its neighbors, right? So you look at what are if you take this point, right? And you look a bit about how many the neighbors of this point, you can see that everything is yellow. If I consider all the neighbors, I would make it yellow. But now, if I consider only one neighbor, which is itself, then I would make it blue. I can go all to the extreme. I can compute k nearest neighbors, where basically it tells you how many neighbors I look around. And then you compute the maximum around all the k's based on how many of my neighbors belong to every class. So, and you can play a bit with the flexibility of the model, as you can see, by changing k. So here we have k equal 10, hopefully. And here you have k with equal 100. Basically, the more of the neighbors I look at, the less the flexible the model. Because basically it's like looking at the overall population in the infinite case, right? If I look at everybody, basically I would classify based on what is the majority class in the whole population. And if I go to the other extreme, basically I decide based on my own class, which is not very useful for prediction later because you would need to at least look at someone. Okay, so let me see. Okay, so in this particular example, as I was saying, we can do a similar plot as the one that we were doing before, where we compute the error rate here on the y-axis versus the flexibility of the model. As I was saying before, the flexibility of the model increases with 1 over k, right? Because the most flexible model is when you have k equal 1 neighbor, and the least flexible model is when I compute it across the overall population, all the training data. So still we have here error like before, and here we have flexibility. And if this is the training error, and this is the test error, and this is the base error rate, which is the optimal one, you can see how this, depending on how you pick k, how the training and the test one works. And of course, again, you have exactly the same trade-off that you had before in terms of flexibility versus generalization. And you would like to be as close as possible to this one. Of course, this is a bit noisy because basically you have a finite data set. In both a finite data set, both in training but also in test. Usually you are not able to evaluate on the overall distribution, but only on a sample of it. Okay, why is the flexibility 1 over k again? Okay, let me try to see if my computer doesn't collapse. These plots are very heavy. Okay, so if I assume that the k nearest neighbor, I assume k equal 1, which is this case, you can see that, again, you can see basically here that basically the solid line is making very weird shapes, right? This is the decision boundary that I would get. And this is basically trying to find a perfect separation. This is gonna be a case of overfitting. If I go now to 10, that looks much more reasonable and it looks much more closer to the base classifier, except for the points where I don't have too much data, like here and here. That sounds like a reasonable value. While if I go to k equal 100, basically for every data point, I'm looking at a very big circle around here, right? And overall, if you would go to k equal to the training data set, basically you would look at the whole population. That is a different question. And of course, this k is making the model, you see the boundary, much less flexible than before. So this is why I say that the flexibility of the model is 1 over k. Okay. So with that, I think I conclude. I think we basically have like 15 more minutes, if I'm not wrong. Did I get it right? Yeah. So maybe we can use this time for you to ask some further questions, because I don't think it makes sense that I'm gonna enter in linear regression for 15 minutes. So questions? No questions?
Yes, I have a question.
Yeah.
Regarding the example with the like the binary classification using bias, was that a hypothetical example? Is that an actual training that we can do? I didn't quite get it well, because I think you said that we needed the probabilities or the more data to do this classification with Bayes.
Yeah. So basically, this is a synthetic example where basically you generate, in a synthetic example, what you can do is to generate the x's from whatever distribution, right? And
Okay.
then once you have generated these x's, you can assume some function of p of y given x, and then generate the labels from this probability.
Okay.
So in this particular case, because we know the generation process of the data, we know exactly what the probability of the label is, and therefore we can get this dashed line that you can see here, which is the Bayes classifier. Sorry, maybe I didn't explain very well myself because my whole computer was collapsing with this figure.
Yeah.
Not very ideal. Okay.
Thank you.
Okay, it seems that these ones are hard to read. I'm not 100% understanding why people are having a problem, right? So basically, everything that you need to understand is that whenever we compute the mean square error between the true output variable and our estimator, this expectation is going to decompose in these three terms, right? And everything I did was assuming that I can compute these terms because I know exactly what y0 is and our predictor. I basically can decompose this MSE, which is the overall term. This is no more than this guy, right? I can decompose it in these two terms, which are the variance and bias, so that this explains why you get this kind of U shape. And the goal in general of your learning, if you want to do a good job, is try to find the bottom of this, the minimum of this U shape when possible, or at least get something that has low variance and low bias, because both of them are gonna bring you to a lower point of the MSE in test. More questions? You are welcome to ask questions both in the chat of the Zoom and also by simply talking. I'm gonna have a look also to the YouTube, which I cannot keep track in general, but it seems that the YouTube link doesn't have questions. It's too many sources of questions.
Maybe another question about the Bayes classifier. It sounded like we could only use it if we had a synthetic data set. But isn't it also, can it not also be used in real world data sets where we just assume that frequency equals probability?
Well, assuming the frequency equal probability, if you can estimate these probabilities perfectly well for every observation in your population, yes, you can recover your Bayes classifier. And actually, the whole point of statistical learning is that under some assumptions, you might make, under some conditions, you might make that asymptotically, as you see an infinite number of training data points, you can make it arbitrarily close to the Bayes classifier. But by arbitrarily close, exactly reaching the zero, not that easy. When I say zero, I simply mean not zero error, but you get the difference with respect to the Bayes classifier arbitrarily close to zero. Because as you saw here, in this example, the optimal classifier, which is the Bayes classifier, still has an error of 0.13. So 13% of the times is wrong because of the overlapping in your data. And there is nothing else you can do there.
Okay, thanks.
Okay, let's go to the nearest neighbor. So, In terms of the expression, if I manage, these figures, I need to figure it out. I think from next week on, there won't be that much of animation. So basically, I guess what people are asking in the chat, Ariana, you are asking about this expression, right? So basically, what it means is that this summatory, this is a sum, that goes over all the samples in your training data set. Not all the samples, you are assuming a k nearest neighbor. So this is basically in your training data set, your k nearest neighbors. And basically what you are seeing is how many of these nearest neighbors, so this sum goes over k, right? For every data point, how many of them, because this is an indicator function, goes into class J. You compute that, as you can see, for every J. And then now you get an estimation of the probability of, you get an estimation of how many of your neighbors, not an estimation, you actually get the counts of how many of your neighbors belong to every group, which when you normalize by the number of k, then this is in order to take the optimization, that doesn't matter because k is constant. Basically, you take the argmax of this with respect to j. So you simply count how many of my neighbors belong to every class, and you select which is the majority, the one that most of my neighbors belong to, and then I get assigned to that class. That is what it means. Is that any more clear? I hope so. So let's see, in the last plot, the green bias and the orange bar, there is no labeling, or I don't see it. That I would need to see if I could move into slides. So in general, there is no labeling here. We might have forgotten. This is clearly test and this is clearly training. In any case, all these plots, they are handmade copies of the book. So all the actual plots with the captions, with explanations, they are in the ISLR book, in the Introduction to Statistical Learning and Applications to R. So don't need to worry too much for that. Yeah. Okay, so the noise. What it is important about the noise is that you never get to observe the relationship between the noise and your variables, right? So you are assuming that there might be a source of noise, and by definition, the noise we are assuming right now that it has zero mean. Let me get out of this. But in general, imagine that you get sensor data, right? Let's imagine that we got sensor data, which measures the amount of light in your room or the quality of my sound. Of course, there is signal. Right now you are hearing me by the microphone, and there is the signal, which is my voice, but there might be some error. But you don't get to see ever my voice without any noise. You get both of them, right? So if you would try to recover automatically what is exactly my voice and clean up any noise that I might make because I move, for example, a lot, that would be what you would be trying to predict, to get a f hat that only recovers my voice. This is not a case of regression, definitely, but this is simply a way for you to understand that the noise is something implicit in your observations that you don't get rid of, but you also don't want to fit. I'm gonna try to skip like the PowerPoint because it's not working anymore. Okay, more questions. Let's see. So in terms of the difference between variance and bias, this is exactly and precisely why you got this as homework. so that you can elaborate a bit further and get a better understanding on that. So simply go to the notes, read the material either in the slides or in the book, and try to make a bit of an effort, try to process, because there is a part where I cannot do for you. I can explain over and over exactly the same, but you slowly will need to look at the plots and try to interiorize every concept that we are seeing here. Okay, in terms of distance, so that of the nearest neighbor. Of course, whenever you decide who are your nearest neighbors, right, you need to decide what nearest means. In this particular case, where you assume, for example, x1 and x2, you can consider a Euclidean space and decide that the nearest neighbors are the ones that are closer to you in terms of coordinates if you would compute Euclidean distance. This is in this space. I'm not gonna really try to even enter in other type of distance. So for now, let's assume Euclidean. Any more questions? Noise is basically redundant info in the data. No, I would say no. Noise is simply noise. So there is no information in the noise. It is simply measurement error, for example, or things that you cannot explain out of the data that you are given. That is why I was talking about the sensor data. Whenever you have a sensor, you might be measuring the signal that you are interested on, but you might also be measuring some other artifacts, like the noise I do when I hit my mic. Yeah, in general, in this course, we are going to assume that the observed data is noise plus actual information. Data is all of it. The data is no more, in this particular setting, we are assuming that the data is a realization of an underlying distribution. And of course, if we are assuming an underlying distribution of y from x, because if you see here, we model P of y given x. Let me try to share this again. Yeah, we said P of y given x. That means that from x, there is not a deterministic relationship to y, but y is sampled according to a probability that depends on x. And this, if I, for the same x0, I could get different realizations of y. And these variabilities, this randomness is somehow what we call noise. This is in the case of Gaussian model, of the categorical case, but in the case of continuous, the good news that when y is continuous, not in the categorical case, you cannot do that, but in the case of continuous variables, you can write the continuous variables as we were doing at the very beginning. If I manage to find this, in somewhere here, yeah. In the case of continuous variables, you can assume that your output variable is some function plus noise. That doesn't hold for any distribution of y, but for quite some family. So this is the assumption that we are working right now. Doesn't need to be always the case. There is always some random, but the fact that the noise is additive doesn't always need to be the case, but we are going to study these cases when we consider y to be real. Let's see if I recover the chat, and then I think we can go. Good. So we are going to enter in the discussion of KNN being parametric or non-parametric in the next few weeks. If it is okay only to read the ESL chapter books, I would say not every so the book that we are mostly following is the ISLR. So there will be not a one-to-one correspondence for every chapter between the two books. So there might be that there are some parts that we study that are presented only in one of the books. So if you have to pick for one, I would say everything will be in the ISLR, but definitely I would say that if you combine the slides with the ESL, that should be probably enough. Okay, so I think with that we can conclude the first real lecture. I hope we get even better over time. I will see you next Thursday. We are Thursday today. Remember that on Monday there will be tutorial, if I'm not wrong. So, and all the assignments are already out. The first assignment are already out. So I encourage you to go into the tutorial so that you work on your assignment and you get also some additional support. Thank you very much, all of you, for being here today and also for asking so many questions. I was not sure whether this would work, but there were quite a few. So enjoy your afternoon and see you next week. I'm gonna shut this down.